The siege tower mechanism had been sitting in the military museum's lower gallery for decades, labeled simply as Ottoman, 17th century. I was there to photograph artillery pieces for a regional history publication, not to question the dating of such heavy equipment. But the ironwork caught my attention immediately. The gearing system embedded in the tower's base was too refined for its supposed age, machined with tolerances that should not have existed in 1650. I knelt beside it, measuring tooth intervals with a caliper. The precision matched industrial specifications from 2 centuries later. The official placard explained nothing that mattered. I returned to the museum the following week with better equipment and a formal research request. The curator, a patient woman who had fielded stranger inquiries over the years, allowed me access to the storage area where the mechanism's detached components had been kept since the 1930s, when the original display was dismantled for a renovation project that never fully restored the exhibit to its former arrangement. What I found in those climate-controlled basement rooms changed the direction of my research entirely and set me on a path I had not anticipated when I first noticed the anomalous gearing. The gearing system was not alone. Attached to it through carefully machined interfaces were bronze fittings with threaded connections, iron conduits with precision bored interiors, and a series of cylindrical chambers that the inventory cards described simply as counterweight housings, purpose standard for siege tower elevation mechanisms. The description had been copied from card to card for decades without anyone questioning whether it accurately described what the objects actually were. But counterweights do not require sealed chambers with precision ground interior surfaces, polished to near mirror finish. They do not need intake valves with adjustable flow restrictors calibrated to fine increments. They do not connect to pipes that lead nowhere the visible structure would require for any conceivable military application involving the projection of force against fortification walls. The components showed a level of integration and sophistication that suggested not a weapon of war designed for temporary battlefield deployment, but an industrial system whose original purpose had been forgotten or deliberately misclassified when later administrators needed to fit acquired objects into existing categorical frameworks that their predecessors had established. The museum's acquisition records dated from 1887, when the mechanism was purchased from a private collector in Vienna for a sum that would have been considerable at the time, and that suggested the collector understood he possessed something unusual. The provenance documentation traced the object backward through 3 previous owners to a fortress demolition in the Balkans, supposedly recovered from Ottoman siege works abandoned after a failed military assault sometime in the 1680s during one of the many conflicts that characterized the region during that tumultuous century. The paperwork was thorough regarding the purchase price, shipping costs, insurance valuations, and the collector's assessment of the object's historical significance as a rare surviving example of Ottoman military engineering. What it did not contain was any technical analysis of the mechanism itself. No engineering drawings explaining how the various components function together as a system. No functional assessment of the gearing ratios, chamber pressures, or flow capacities the design could sustain. Just a brief description that had been copied from one inventory card to the next for nearly 2 centuries. Siege tower drive mechanism, Ottoman period, believed 17th century, condition fair to good. I measured the gear teeth with precision instruments the original catalogers could not have possessed, and that would have been unavailable to the craftsmen supposedly responsible for the mechanism's construction. The involute profile of each tooth, the curved shape designed for smooth power transmission between meshing gears, matched engineering standards that would not be formally codified in technical literature until the late 19th century. The tooth spacing showed variation of less than 0.1 millimeters across the entire assembly, a level of manufacturing consistency that modern CNC machines achieve routinely. But that hand-forged ironwork from the 1600s should never have approached, regardless of the skill of the individual craftsman. A metallurgical study conducted in 1956, buried in the museum's conservation files among routine condition reports and pest control assessments, noted the unusual composition of the iron alloy from which the gearing had been manufactured. The carbon content and trace element signature did not match known Ottoman foundry practices from any documented period that researchers had studied. The study recommended further analysis to determine the metal's true origin and manufacturing method. No follow-up study was ever conducted. The recommendation sat in the file, apparently unread for decades, until I requested the complete conservation history and discovered it among papers that showed no evidence of having been examined since their original filing. The museum's classification system grouped the mechanism with other siege equipment displayed in the adjacent galleries: battering rams with iron-shod heads designed to break down wooden gates, scaling ladders with reinforced rungs capable of supporting armored soldiers, mobile wooden shields designed to protect advancing infantry from arrows and stones, standard medieval and early modern military hardware of the sort every military museum collected and displayed. But the engineering complexity of my subject set it apart from everything around it in ways that should have been obvious to anyone who examined the objects with technical understanding. A battering ram requires mass and momentum delivered through simple pendulum motion against a target. A scaling ladder requires length and stability when leaned against a vertical surface at the proper angle. Neither requires precision gearing with involute tooth profiles ground to industrial tolerances, sealed pressure chambers with interior surfaces finished to standards exceeding contemporary machine work, or the elaborate valve system I documented over 3 days of careful examination in the storage basement. The official interpretation assumed a purpose: siege warfare, that the physical evidence could not support under any reasonable engineering analysis. The mechanism was classified as what it was not because someone had determined what it was for. But because the fortress location where it was found suggested military applications to people who lacked the technical background to recognize that the device could not have served any such function effectively. I found a similar discrepancy in the fortress reconstruction reports from the original excavation site, documents I obtained through correspondence with regional archives that maintained records from the period. A military engineer writing in 1884, tasked with surveying the ruins for potential restoration as a historical monument, described the recovery of mechanical components from beneath the collapsed wall section where the siege equipment had supposedly been abandoned 2 centuries earlier by Ottoman forces retreating from a failed assault. His field notes mentioned drive assemblies of unusual refinement and housing chambers whose function remains unclear despite thorough examination by myself and colleagues with engineering backgrounds. He recommended preservation of all components for scholarly study before any restoration work proceeded that might disturb the context in which they had been discovered. The components were sold to the Vienna collector 3 years later, apparently with the blessing of provincial authorities who saw no value in machinery they could not identify, and no reason to fund the scholarly investigation the engineer had recommended. According to the standard historical narrative taught in military academies and reproduced in museum exhibits worldwide, Ottoman siege technology reached its peak in the 15th and 16th centuries with the great bombards that breached the walls of Constantinople in 1453. Massive bronze cannons, some requiring hundreds of oxen to transport and crews of dozens to operate, represented the cutting edge of siege warfare for their era and demonstrated Ottoman engineering capabilities at their height. By the 1680s, when this mechanism was supposedly built, gunpowder artillery had rendered mechanical siege towers largely obsolete for any practical military purpose. Fortifications throughout Europe had evolved specifically to resist cannon fire through angled walls and star-shaped designs. Assault tactics had shifted to accommodate firearms and field artillery. Yet here was a mechanism far more sophisticated than anything the earlier peak period had produced. Recovered from a site where it supposedly served a military function that no longer made tactical sense for any competent commander to employ against fortifications designed to withstand very different threats. The chronology did not fit the known development of siege technology. The engineering precision did not fit the manufacturing capabilities attributed to Ottoman foundries or any other contemporary metalworking tradition. The purpose remained unexplained by any military application I could identify or any historian I consulted could suggest despite extensive discussions about possible uses. I began searching for comparative examples in museum collections and archive catalogs across Europe and Central Asia, regions where Ottoman military activity or influence had extended during the relevant centuries. If this mechanism was unique, an isolated anomaly produced by some exceptional craftsman whose individual work exceeded the capabilities of his contemporaries by margins that seemed implausible, then its unusual characteristics might be dismissed as misattribution or circumstantial oddity, not warranting further investigation. But if similar devices appeared elsewhere, credited to different builders in different periods, serving different military campaigns under different imperial banners, the pattern would demand a fundamentally different kind of explanation that could not be accommodated within existing historical frameworks. Within 6 months of focused research, conducted through correspondence, archive visits, and examination of digitized catalog records that had recently become available through various national digitization projects, I had identified 11 comparable mechanisms in museum collections spanning from St. Petersburg to Dresden to Tashkent, across thousands of kilometers and several centuries of supposed construction dates. Each mechanism carried different dating in its catalog entry. Each was attributed to different military forces, operating in different centuries under different imperial systems with different technological traditions. Each shared engineering characteristics, gear tooth profiles, valve configurations, chamber specifications, that should not have been possible if they were truly built independently by different cultures separated by substantial distances in both time and geography. The pattern emerged most clearly in the gearing systems, which had survived better than the wooden structural components that had originally housed them and had been discarded or destroyed during the various recoveries and relocations that brought the metal components into museum collections. A mechanism in the St. Petersburg Military Museum, labeled as Russian siege equipment manufactured for Peter the Great's campaigns in the 1720s, showed gear tooth profiles identical to the Ottoman example within my measurement precision. A device in the Dresden Armory, attributed to Saxon military engineers working under Augustus the Strong in the 1690s, used the same valve configuration with matching thread specifications on the adjustment screws. A fragmentary assembly in Tashkent, described as Timurid period work from the early 1400s, contained bronze fittings with thread pitches that matched both European examples despite supposedly predating them by 3 centuries. Different empires claiming these territories across different centuries. Different military campaigns providing historical context for their supposed deployment. Different museum curators assigning construction dates based primarily on where objects were found rather than technical analysis of what they actually were. Yet the same underlying engineering signature repeated across the entire sample, as if manufactured to a single specification and distributed across a continent before the modern states that later claimed them had come into existence. An engineering journal published in Paris in 1862 contained detailed sketches of a siege mechanism recovered from fortification works in Samarkand during French scientific expeditions through Central Asia. The author, a military engineer accompanying the survey team who possessed the technical background to recognize anomalies that antiquarians and historians might overlook, noted that the device appeared far older than the fortress itself, possibly predating all current regional powers by a margin he could not estimate with confidence. He described internal chambers arranged in concentric rings like growth patterns in a tree trunk, connected by conduits whose function he could not determine through visual inspection or comparison with any European equipment he had previously examined during his career. The configuration matched what I had documented in the museum basement. His marginal notes expressed puzzlement that equipment supposedly designed for demolishing fortification walls should contain elaborate hydraulic channels that served no visible structural or military purpose whatsoever. A Russian military report from the same decade described similar mechanisms discovered during fortress renovations along the Volga River. The author called them ancient machinery of unknown origin, now classified as siege equipment for administrative convenience in the absence of any better category. The phrase sat quietly in a paragraph about inventory procedures and storage requirements, almost invisible among bureaucratic language about facility management. Administrative convenience. The mechanisms had been assigned a purpose not because evidence supported that interpretation, but because the imperial classification system required every item to fit an existing category before it could be properly stored and accounted for. Siege equipment was an available category. The machinery was found in fortresses. The classification was applied without further analysis that might have complicated the administrative process. I located an atlas published in Vienna in 1818, one of the last major cartographic works to use the older geographic conventions before the Congress of Vienna reorganized European territorial claims and subsequent editions updated their nomenclature to reflect new political realities. The map labeled the entire region, stretching from the Volga River to the Pacific Ocean, as Tartary, with subdivisions marked for Great Tartary, Independent Tartary, and Chinese Tartary, depending on which power nominally administered each zone. Several of the fortress sites where mechanisms had been recovered sat along routes marked with heavy black lines that the Atlas legend identified only as principal roads, without attribution to any builder or maintenance authority. Trade corridors and transportation networks that clearly predated the political boundaries drawn over them by later imperial administrators. Infrastructure that the Atlas documented as existing without explaining who had built it or when it had been constructed. The mechanisms appeared at nodes along these routes, at river crossings and mountain passes and urban centers where goods and people would naturally concentrate during commercial activity. The geographic distribution made no sense for siege equipment, which should cluster at strategic military positions controlling defensive terrain rather than commercial intersections facilitating trade. Alternative researchers who study what they call Tartarian infrastructure, a body of work dismissed by mainstream academic historians, but persistent in certain investigative communities that operate outside institutional frameworks, often argue that many military installations across Eurasia did not build their foundational equipment. They inherited it from predecessor occupants, repurposing sophisticated machinery for cruder applications that fit the technological capabilities and conceptual frameworks of later users who could not understand what they had found. The classification of these mechanisms as siege equipment would fit that hypothesis with uncomfortable precision. Devices originally designed for purposes their inheritors could not comprehend. Assigned military functions simply because fortresses were the structures where they happened to be discovered when modern inventory systems required categorical assignment. If the hypothesis was correct, the siege equipment label was not merely inaccurate, but actively misleading, a barrier to understanding rather than a pathway toward it. Late on a Thursday evening in early autumn, working through a backlog of catalog requests and correspondence with archivists who had been helpful in locating obscure materials, I located a set of technical drawings in a private collection maintained by a family in Munich. The papers had been removed from an Austrian imperial military archive during the chaos of 1945, preserved by a collector whose grandson now maintained the family holdings in climate-controlled storage. The drawings depicted a mechanism nearly identical to the museum specimen in external configuration, but with one critical difference that changed everything I thought I understood about these devices. The original engineering analysis notes were intact, attached to the drawings rather than separated and filed elsewhere, as typically occurred when military archives were reorganized by administrators who did not understand the technical significance of documents they were processing. The analysis document was dated March 1843, prepared by a military engineer named Hauptmann Karl Venzel, who had been tasked with analyzing equipment recovered from a demolished fortress in Transylvania the previous year. His assessment, written in precise technical German with measurements provided in both metric and traditional units for clarity, was unambiguous in its conclusions after what appeared to have been thorough examination. The device was not a siege engine in any functional sense. The gearing system was designed not to deliver mechanical force outward against an obstacle, as any weapon must, but to receive and regulate force from an external source, converting variable input into controlled output suitable for powering additional equipment. The sealed chambers were pressure vessels rated for loads far exceeding any water system documented in contemporary engineering literature. The valves controlled flow rates with adjustment precision matching the governors on contemporary steam engines. The conduits connected to intake and exhaust ports that would have been completely invisible once the mechanism was installed in permanent housing within a building foundation rather than mobile military equipment. Hauptmann Venzel concluded that the device appeared designed to harvest mechanical energy from a source he could not identify with confidence, converting rotational or oscillating force into regulated output that could power additional equipment through the conduit system. He speculated about water wheels or wind capture as possible input sources, but noted that the specifications and pressure ratings substantially exceeded any such system documented in contemporary engineering literature or his own experience examining hydraulic installations throughout the empire. His final observation was almost casual in its implications for historical understanding. Whatever powered this machinery, he wrote, it was not built by the forces who later occupied the fortress and from whom we recovered it. The technology is beyond their demonstrated capabilities in every particular I can assess. The document had been filed in the Imperial Archive, assigned a reference number, and apparently forgotten within years of its completion. The mechanism it described was eventually reclassified as siege equipment to match the standard inventory categories and sold to a collector who found its mysterious origin romantically appealing. Hauptmann Venzel's careful technical analysis was never published in any engineering journal, never cited by subsequent researchers investigating similar materials, never incorporated into the official understanding of what these devices represented or how they actually functioned. By late summer of the following year, having assembled substantial documentation and established relationships with cooperative museum staff, I had obtained permission to examine the museum mechanism under conditions the original catalogers never attempted, and that modern conservation protocols rarely allowed researchers to pursue. Using fiber optic cameras threaded through inspection ports that previous examiners had dismissed as simple ventilation holes, I documented the interior surfaces of the sealed chambers in detail. What I found confirmed Hauptmann Venzel's 1843 analysis across a century and a half of intervening scholarly neglect. The chambers were not counterweight housings designed to store mass for mechanical advantage, as the inventory cards claimed. They were pressure regulation systems of considerable sophistication, with internal baffles arranged in spiral configurations designed to smooth pulsating input into steady output flow suitable for powering precision equipment. The valve assemblies controlled not water or air, as standard hydraulic systems would require, but something substantially denser based on the port dimensions and flow restriction specifications I measured. Residue analysis conducted by a sympathetic metallurgist who agreed to examine samples without asking too many questions about their source-detected trace compounds consistent with mercury amalgams in the valve seats and chamber surfaces. The same materials appeared repeatedly in Tartarian research literature, describing devices that some alternative historians interpret as atmospheric energy collectors. I photographed scoring marks on the interior chamber surfaces that showed characteristic patterns of operational wear accumulated over extended service periods. The mechanism had not been built and immediately abandoned, as the siege equipment interpretation would require for a weapon deployed at a fortress that supposedly fell to assault shortly after construction. It had been used continuously, maintained by someone who understood its function and had access to appropriate materials for upkeep, and eventually decommissioned through deliberate shutdown procedures rather than battlefield destruction. Physical evidence eliminated the siege equipment interpretation entirely. Whatever this device was designed to accomplish, demolishing fortress walls was not among its intended functions. A conservation report from 1923 noted that workers conducting basement reorganization had discovered additional components stored in unmarked crates that appeared to belong with the main mechanism based on matching materials and manufacturing marks. Iron housings with precision bored mounting holes, bronze connector assemblies with the same thread specifications documented elsewhere, fragments of what appeared to be a heavy mounting frame designed for permanent installation. The report recommended formal investigation. The components were labeled miscellaneous hardware, fortress origin, siege equipment related, and returned to storage. I found them on the same shelving units where they had been placed a century earlier, still uncatalogued. The mounting frame fragments revealed something the isolated mechanism could not have shown. The device was designed for permanent installation, anchored to building foundations extending below ground level. Bolt patterns matched architectural requirements in engineering drawings of major civic infrastructure, not fortresses. Not military installations, buildings constructed for permanent urban functions. By early autumn, I had assembled documentation from 43 mechanisms across 12 countries spanning 4 continents. The North American example surprised me most. 19th century photographs of mechanisms recovered from pre-colonial ruins in the American Northeast showed identical gearing profiles, matching configurations, and the same absence of plausible military application. A railway engineer's journal from 1878 contained a passage that stopped me cold. We found machinery in the foundation excavation whose purpose we cannot determine and whose manufacture appears beyond our present methods to reproduce. The geographic distribution followed patterns making no sense under siege equipment interpretation. The devices appeared at nodes along trade routes, river crossings, and urban centers. Locations coincided with sites older maps had marked as significant before modern borders were drawn. A travelogue from the 1870s described massive iron gearing visible in a demolished building's foundation, which locals attributed to the old empire whose name had become a source of confusion among elderly residents. The elders could not agree on a name. Some called it the Tartar Kingdom. The machinery itself was the only point of consensus. It had been there longer than anyone remembered. I returned to the museum on a clear morning in early spring. The mechanism sat where it had for over a century. I thought about Hauptmann Venzel, the French author in Samarkand, the Russian officer who recorded administrative convenience as the basis for classification, the museum workers in 1923 who found components and returned them to storage without investigation. The pattern was not conspiracy. It was institutional inertia. Anomalies were encountered, recorded, classified into existing categories, forgotten. Mysteries accumulated in archive basements, never synthesized, never questioned. The evidence could not prove a Tartarian empire, but it demonstrated something significant. Sophisticated technology with consistent engineering signatures had appeared across 4 continents in contexts making no sense under assigned interpretations. Devices had been systematically misclassified, their purposes obscured by frameworks that could not accommodate physical evidence. Whatever these mechanisms were designed to do, knowledge had been lost through processes prioritizing classification over understanding. The devices remained, too durable to deteriorate, too precisely engineered to dismiss. They sat in museum basements and fortress ruins, bearing witness to capabilities the official timeline did not acknowledge. I photographed the mechanism one final time. The teeth still meshed perfectly. The chambers still held pressure. The engineering endured. Somewhere in storage rooms across 4 continents, remnants of something older continued to wait, cataloged under categories obscuring their nature. Labeled with dates, physical evidence contradicted. The mechanisms remembered what records had forgotten. For those willing to look past placards, the evidence remained where it had always been. Silent, patient, waiting for recognition. The iron and bronze remember what the classifications have obscured. And for those patient enough to search, to carefully measure, to question the convenient labels that forestall genuine investigation, the truth patiently waits beneath the deceptive surface of accepted history.